Good morning everyone. This is the topic from the analog integrated circuit. The topic is integrated. So integrated is a circuit to integrate the input. So simply we can say that we can apply a sine wave signal to the integrator. We got the cos waves, and we are applying any square wave signal. We got the triangular wave signal or spike signal. So first we will introducing the circuit diagram of the integrator using op amp and making the equation for the integrator. Then we can find the drawback of the integrator or ideal integrator, and finally we are concluded with the practical op amp. Then plotting the frequency response of the basic integrator and also the practical integrator based on the S domain. So starting from the integrator basic diagram. So op amp Pout and the input resistance R1. So the one of the equivalent resistance value are compensate, that is equal to R1 in the case of ideal. So we are applying the input. This is Vi of t, because we are applying the input is a time varying signal. So this is a closed loop system. Just replacing the capacitor, just replacing the resistor Rf by a capacitor Cf. So this is the block diagram of circuit diagram of the integrator. So we can apply the two input levels Vb of t and Vi of t. So we know that the equation, simply we can apply the input current Ii. So when Ii is equal to the branch currents, this one is the Ib and some of the currents coming to If, and the small amount of current is coming to the input of the op amp, because the input resistance of the ideal op amp is very high. So we can denote Ib plus If. So we already know that the value Ib is very negligible, so we can denoting the Ia is approximately equal to If value. So Ia is equal to If. So now making the equation for Ia and If. So Ia is Vi of t minus Vi of t divided by the resistance value R1, that is equal to the capacitor Cf d by dt of V0 of t minus of Vi of t. So we can predict with the check down concept, that is whenever the Vb of t is connecting to 0 value, so there is no current is coming. So whenever Vb of t is equal to 0, V of t is also 0. So now we can write the equation become Vi of t by R1 is equal to Cf of d by dt of V0 of t only. So by virtual ground concept, VA of t equal to VB of t equal to 0. So now the equation become VA of t. Now the equation become VA of t by R1 is equal to capacitor CF d by dt of minus V0 of t. So this is VA of t and this is V0 of t. VA of t minus V0 of t. So the equation become CF into d by dt of V0 of t. So integrating both sides. So integral of VA of t by R1 is equal to CF of t by dt of minus V0 of t. So the integrating starting from 0 to t. So now the equation become, so whenever 0 to t, CF of d by dt of minus V0 of t, we are taking CF is a constant value. So 0 to t d by dt of minus V0 of t, we got the V0 of t only. So in this case, we can find the output voltage of the integrator is V0 of t is equal to minus 1 by R1 CF, minus is coming here, minus R1 CF of 0 to t VA of t plus, there is a 0 value is here for the integration. So that is the 1 whenever the integration is takes place. So one of the thing is t value and the next limit value is 0. So V0 of 0. So V0 of 0 is denoting C. V0 of 0 denoting the constant value C. So C is a integration constant and it is proportional to V out at t is equal to 0. So negative sign is the integrator is connecting to the input is connecting to the inverter terminal of the op amp. So now we can draw the waveforms of the different input signal. So this is the input signal, there is a sine wave signal we are applying. So what about the output voltage? So whenever the V out, what about the V out voltage? Whenever the input is a sine wave signal. So in this case, whenever the input is rising condition, so there is a capacitor is charging, but there is a negative voltage. So it is coming to like this and moving to like this is happens. So whenever we are applying the input is a square wave signal, what happened the VI and V0 of t. So what happened the output voltage? So whenever the rising edge is going to be the negative, so this is the point is here. So starting from the same amplitude like this and going to the starting point and it is moving to the this side. So this is happening. So slope is going to be 1 value. Slope value is 1. So this is a simply what is the integrator. So how to make the integration, this equation is very important. Need to make the analysis, very important equation. So the input is connected to the inverting terminal, and arc comp is a very negligible for compensating the input loading. So by applying the virtual ground concept, we not consider the arc comp value. So whenever the virtual ground concept is coming, so we will take the VA of t and V0 of t is here. So we will find the equation by integrating the part by, because the equation for the capacitor is C into d by dt of V out of t, or V of t is generally. So in this case there is a V out of t is here. So we can denote this one is a V out of t. So now we can find the frequency response of the ideal integrator and also the practical op-amp. So in this general diagram, whenever the Vin input is 0 value, Vin is 0 voltage, what happened? So the 0 voltage is coming, the capacitor is in the blocking condition, that is Vin is a 0 voltage, so the capacitor is in the open condition. So whenever the Vin is equal to 0, the integrator works as an open loop amplifier, because the capacitor CF acts as an open circuit. That means XCF is infinity. So in this case, the input offset voltage of the op-amp and the part of the current IA is producing a error voltage in the output. So in this case, there is a error voltage is happens in the output because of the input is a low frequency signal or 0 voltage, because of the XC is infinity. So making an voltage, error voltage happening by the sum of the input current IA and also the particular offset voltage. So we will get the error voltage is here. So we can determine the frequency response of the basic integrator based on the frequency response. So for the frequency response, we can plot the frequency response. So the operation of the integrator can also be studied in the frequency domain. The phasor notation can also be written from the basic equation of the integrator is V0 of t is equal to minus 1 by R1 CF integral 0 to t Vi of t dt plus C. So we can write the equation in S domain. The t is replaced in S by minus 1 by, the integration is replaced by 1 by S R1 CF into Vi of S. So in the case of steady state, S is denoting to j omega. So we can write the equation become V out of j omega is equal to minus 1 by j omega R1 CF into Vi of j omega. So we can write the gain in magnitude, that is gain that is equal to V out simply by V in. So in the case of j omega, so that is equal to minus 1 by j omega R1 CF. So that is equal to 1 by j is minus j is, in the case of mod is going to be 1. So j R1 CF. So omega become 2 pi f. So we can write the frequency response of the basic integrator, that is denoting by the FB. So equating the equation, that is 1 by R1 CF, that is 2 pi F into R1 CF. F is denoting the FB value, so the equation become 1 by 2 pi R1 CF. So this is the B is the basic integrator, so the frequency is denoting the FB. So we can put this equation number 1. So we can draw the frequency response simply by like this. So this one is the gain. Gain is V out by V in dB. So this is the frequency in log value. So in this case, the ideal, whenever the zero input is or zero frequency signal is coming, what happened? The capacitor CF is in the open condition or X is infinity. So that is acting like a open circuit or open loop condition, simply like this. So the R1 is here, so there is our input. So the R1 in the low frequency, the CF acting like a open. So this is like a open loop configuration. So whenever the open loop configuration, the gain is very high, or in the case of gain is infinity. So gain is infinity, so we can denote the infinity. But that is in the theoretical condition. But in the practical condition, there is a value is here, so denoting the value is here. So this is the value. So further increasing the frequency, what happened? The capacitor XC become is proportional to 1 by F condition. So whenever the frequency is increasing, the XC is decreasing 1. So the output is going to be decreasing 1. So whenever the frequency omega is equal to 0, the magnitude of the integrator is infinity. Or for the DC values of the input signal, the capacitor CF acts as an open circuit. So there is no negative feedback. So in practical case, the gain does not goes to be infinity value. There is rather than the output of the amplifier going to be a saturation at a voltage. This is the point I am denoting the saturation voltage. So close to the op-amp, positive or negative power supply depending on the polarity of the input signal. So then we will get the response is here. So this is the ideal op-amp condition. So now we need to think about the practical op-amp condition. So why we are moving to practical op-amp condition is that whenever the zero frequency or DC value or a less than a value, what happened? The gain is going to be infinity. That is one of the problem in the ideal integrator. So we need to overcome this problem. So we need to implement another or modified circuit is called practical integrator. So in this is the FB. So overcome the difficulties of the low frequency condition of the basic integrator, we will think about the practical integrator. In the practical integrator, it's also called the lossy integrator. So in the lossy integrator,